So by the way, I'm having trouble with the recording. Last lecture, I thought I recorded again. I didn't get my sound recorded. So I tried again. I got an external microphone and also the computer microphone. The Zoom will use the external, and my recording software will use the internal. So hopefully today everything will be good. I tested. Okay. All right. So let's continue in here. So basically, we're going to consider these welded joints, okay, as a combination of base material and electrode. Okay. And then, as I mentioned, in order to do that, we need to get the material property, right? So for electrode material, we use table 9-3, and this is a table we will use to get the electrode material. And I explained roughly how you can get the properties by reading just the electrode numbers. The first 2 or 3 digits give you the tensile strengths. And the second column, third column here give you the yield strengths. Okay. And of course, the base material or the parent material So those are the materials. You can easily look it up from appendix in the textbook. So there are many appendices. Okay, so what you're looking for is SUT and SYT, right? Okay, so then I'll explain why do you need both, right? Because we need to consider a mixture of materials here. And the next step is you will look at the welding code. Okay, so this is defined by AISI, and this essentially is table 9-4. So I'll show you the welding code in 9-4. This is a 9-4 at here. And for this welding code, okay, so let's read it and put it over here. Okay. And for this welding code, they refer to different type of weld, but in our case, since we're going to mainly focus on the fillet weld, so we'll look at this column here, right? So the welding code that here refer to basically, so you see permissible stress given here. So this is essentially the permissible strength value, right? So as you can see here, the permissible stress, you have actually 2 different permissible stress. One is 0.3 SUT. Okay. Another one, if you look at reading to the footnote, it also says the shear stress on base metal should not exceed 0.4 SY of a base metal. So we need to consider both of these at here, because we're considering not just the electrode, but also the base material. So we're going to use both of these equations to find out the permissible stress, right? So the process is, okay, you first of all, okay, you need to identify the SUT, okay, find the minimum SUT from the electrode material, and also from the base metal. Base metal, if you're joining 2 different base metals, then you probably have SUTs for two different SUTs and SYT, right? So an electrode here. And similarly, you find the minimum value for SYT electrode and also the base metals. Right. So once you find the two minimum in here, then we substitute SUT, SYT into the welding code equation of these two here. And then I do another minimum basically. Okay. So what's out of this, right? That will be your permissible stress. Okay. So this is the approach based on our consideration, as I said it, considering the whole weld joints as a combination of base metal and electrode material. Okay. Now, of course, if you just want to analyze the electrode, okay, without thinking of or without considering the base material, then your SUT, SYT, right, you won't have to consider the base metal. That will be just the from the electrode material. Okay. Similarly, if you just want to consider the failure of the base metal, then you just actually use the base metal here, but you will use this code, welding code, right? So that is the process we're going to do, okay, from for the next example. We'll look at it, okay? Yeah. Okay. So let's look at an example here, okay? So this permissible stress, okay, you'll compare that with the shear stress tau. So that's the process. Compare this with this and see if you get a safety or not. Okay, so let's take an example. Okay, feel free to ask questions. So in this example, I'm going to look at fillet weld, and we're going to join basically two different plates. Okay, and we will do a fillet weld. Okay, and the welding symbol will be like this. Okay, it's a bit too long. Let's make it a little short here. Now here's a welding symbol, and this is the part you will have to be able to read this welding symbol, right, to get the information out of it. So what this means, if you recall, that basically means you have a two fillet weld, and on both sides, okay, the leg height is 5/16 inch. Some of the dimension in here, this is 2 inch, and this is also 2 inch, and this is 6 inch. Then you have a load F at here. Okay. All right. So the two part of the question. First part of the question is, let's just suppose that you already know the permissible stress. So the allowable one is 20 KSI, and then we want to calculate what will be the maximum allowable load F, okay, for this case. And second part of the question is, okay, will be a more of a practical situation. So say you have an electrode E7010, and this bar at here is 1020 hot load, and the support is 1015 hot rolled. If this is the material, then the question is, what will be the maximum allowable load, okay, for the F. So let's solve for the first part at here, okay, and the second part, which basically apply this equation in here. Okay. To solve this kind of question, okay, step one. Right. Step one is always to identify, is it an in-plane loading or out-of-plane loading. Okay, this is very important because if you got the first step, wrong, then you literally got you will have the rest of the calculations all wrong. Okay. As we explained, okay, in the previous lecture, in-plane and out-of-plane refer to the relationship between the load F and the Weld group. So if you can place both of the Weld group and F in the same plane, they're called in-plane. Otherwise, they're going to be out of plane. Okay. So in this case, my Weld group is over here and F over here. Clearly, right? Both of these can be placed in the same plane. So this is the in-plane loading. When you have an in-plane loading, right? Your table, okay, for finding the polar moment area, and it's going to be different from the outer plane, which will become just the second moment of area. Okay. So now it's in plane, so then we can go to the correct table. And if you recall that, that's the table 9-1, okay, for us to identify the J value. Okay, and this table is a JU value. Okay, so first step, once you get identify this now, right, and then you go look at this Weld group. Okay, you draw the Weld group here. In this case, you can just draw two horizontal parallel lines representing this Weld group. Okay. And if you look at the table 9-1, okay. So table 9-1, you don't have two horizontal lines, but you do have a vertical, but this is actually the same because of the polar moment area. So I can recycle whatever information in this row at here, and I'm gonna label this is B value, and this is your D value. Right? So very much like this is B, this is D. Yeah. Centroid is given by X bar and Y bar, and JU is given by this formula at here. Okay. Okay, centroid is over here, right? And JU, I'll just rewrite it at here. So JU, okay, equal to D times 3B squared plus D squared over 6. Okay. According to the dimension, B is 2 and D is also 2, right? So substitute into here, you get 5.33 inch cube. Then you can get your J value. The polar moment of area is 707 H times JU. H, that you have to read it from the given notation symbol, which is 5/16. So now substitute JUJ into here. We get our J 1.18 inch to the power 4. Okay. Alright, so now get this. Then the next step is for so let's see here, step 2. So this is calculate shear stress. to calculate the shear stress, as you remember, essentially I first identify the critical location or location that can give you the maximum shear stress. So obviously going to be in this location in here, because you would have basically a torque generated by the load F, and also there will be a shear stress due to the F. So we will have basically one is our so-called primary shear, tau prime, and then you also have a secondary shear, tau double prime. Tau double prime basically is due to so these two should be perpendicular. It's due to this torque. Okay, but as you recall, instead of getting tau double prime, so what we do is we separate the tau double prime into two components. We call it tau double prime x, and then another one over here, tau double prime y. So two components for the tau double prime. Then we calculate tau x double prime, tau y double prime based on one of this distance here, and the other one is this distance. Okay, yeah. So I'm going to write the bottom here. Okay. So first step, primary shear. Tau prime, and that's due to the F and over the throat area. So throat area, you can also get it from this table, which is 1.41, technically 1.414. Okay, because that's basically there are two strips here. Okay, so but that's okay. Yeah. So A equal to 1.414 and H, right, times, okay, so times D, right? D is this times D. So I do have everything. We don't have F yet, right? F is something that we need to figure out. So I'm gonna keep the F here, but the overall this is 1.13 times F. Okay, that's primary shear. Secondary shear. Okay. Secondary shear, as I mentioned, you need to calculate this separately. One is the tau y double prime, tau x double prime, right? And then here is the torque. Okay. So apparently, if I do the calculation, tau x double prime, and that's t times this distance. So let's call this R1, and divided by the polynomial area. And R1 is just half of the dimension B, right? So T times half of B over J. So substitute everything into this, and you will get 5.93 F KSI. Okay, so that's tau x double prime. Then next is tau y double prime. So tau y double prime is T times this distance, and that's R2. So R2 over J. Now R2 is half the dimension B, so that's a D. Okay. Let me see, there's a question in here. You're finding the shear stress at the critical location for the weld group. The weld group, of course, consists of two strips of weld. Right. the weld group, right, is the 2 strips, and this location here is the location that will give you the maximum shear stress, because that's the longest distance, right, from here to here. Okay. Good. All right. So now bottom line, this R1, R2, huh? Okay. This is essentially your centroid dimension. So let's say if this is x-axis, this is y-axis. So your x bar and y bar, right? That's what give you this centroid of this, right? Actually, sorry, this should be x bar should be the R2, R2 is x bar, and R1 is y bar. Okay. And as the dimension given here, right? So you have x bar and y bar. Yeah. So that table is very useful to find the correct numbers, okay, based on dimension. So for example, right, in this question, it probably doesn't make difference because both B and D are 2. If let's say this is 2, this is 3 or 5, okay, so then you have to identify the numbers correctly. Which one is B, which one is D? Okay, now you once you get this, and then you calculate the total shear stress at the location. Total shear stress, what you do is you add up all the y direction and add up all the x direction, then you take square of that and add the sum of the square and then take square root. So this is tau primary shear, and the secondary shear, that's y direction. Then you have the x direction. So plugging, oh sorry, I haven't done this right now. So this is 5.93 F KSI. Okay, so plugging everything, simplify, and you get 9.22 F KSI. Okay, so this is your total shear stress. And the next step, once you get this, then we're ready to answer part A and then part B. For part A, all you need to do is, right, you compare the total with the allowable one. Okay, so basically you need this 9.22 F, okay, to be the same as maximum, to be the same as the allowable tau allowable, which is 20 KSI. Okay. Then you solve for F, okay, and that gives you 2.17 kip or 1,000 pound force. Okay. That's part A. Okay. So for part B, okay, we need to start almost like from the beginning. Part B gives you the material property, okay, for electrode and also base metal. So first step, you need to list all the material properties first. We got 70-10 for the electrode, and if you look up the table for electrode E70 series, and you get SUT with 70 and SYT is 57. Okay, so that gives us SUT 70 KSI and SYT 50 KSI, or 57. Okay, that's electrode. And then the base metal, one of them is 1020H hot rolled. SUT, if you look at your appendix, this is 55, and SYT is 30 KSI. The other base metal, the support, is 1015, this is 50, and this is 27.5 KSI. Okay. So once we get this, then we'll apply our formulas to get the minimum ones, okay, based on the welding code. Okay. So SUT, right, first is the minimum out of all of three at here, which is 50. And SYT is the minimum out of these three, and that's 27.5. So then you get your from welding code, your allowable one is the minimum, okay, between 0.3 SUT and 0.4 SYT. And then you multiply these together, you get basically out of here this 11 KSI. Okay. So if you do a calculation, I believe that will be this one is the minimum here. Okay. All right, last step. Let the allowable one equal to the actual shear stress and solve for F. So the 11 over 9.22, so 1.19 KSI, or kip, okay, 1,000 pounds. All right, so this is the second part of the question. Okay. Now just a quick comment before we move on. Okay. Different variations of the question, right? So it would be this. So for example, right, different variations. The question is maybe given, okay, given material and the load F, or maybe torque, who knows, right? Depends on the, okay, or torque. So given material and given your load, and then, okay, and also given, let's see, and also given the type of weld. So basically, like in this case, you have up and down, right? All of the welds here. So this in this type of question, if you're given all of this, then you may be asked is, right, what will be the basically the minimum leg height H. Okay, so given the load, given the material, and what will be the welding leg height H in order to satisfy the design requirements. This is also a very typical type of question. Okay. So basically in this case, you need to design your H properly. Okay. This is your H head here to satisfy the design requirements. All right. So, take a look at the assignments. Okay. There and also tutorial. I believe there are a few more questions, type of questions on welds. Okay, with different type of geometries. So any questions so far? I think that's what I'm going to cover. Okay, all about for welds. Any question? Okay, no question. All right. Now let's look at the last mechanical component, which is mechanical springs. Okay. Oh, actually, I need to, before we move on, I need to point out one thing. I had a student email me, Daniel, and he has had extensive experience in welding. This is, I really appreciate, actually. This is sometimes my own student probably knows more practical issues weld, or not just weld, maybe many other things, right, than a university professor. Okay. I've got an audience between me. I never played with a weld. I can theoretical, I can teach you, but if you want me to weld something, right, that's out of my reach. So one of the email he pointed out is the heat affected zone from welding is very likely to be location of failure, as it is weaker than both the base material and the weld. And therefore the geometry and the material of the base metal is important to analyze, as well as the weld. Welds are typically much stronger than the material adjacent, but they can be designed to be the location of failure, similar to how a key is designed to break before a shaft. So those are really good points at here. So basically you need to pick the right feeder material or electrode right before you start your job. If you look at my lecture notes, I do have some additional material. You can look at it. At the end of the lecture notes, I have a table from ASI size specification. Essentially, it has the recommended the matching feeder and the base metal. Right. There's also a couple other issues as to what would be the suggested the height of the fillet weld, right? In reference to the thickness of the plates. Okay, so take a look at this. Okay, those are just some additional materials. All right, let's continue on the mechanical spring. Spring is a very important mechanical component, and you have seen that type of things in many different applications. I do have a few pictures I want to show you here. So one of the common things you see a spring, right, is in the car suspension system. And the importance of that is when the car tire goes through a bump, then the spring will absorb this shock, okay, and it will release the shock once it passes the bump. So the passenger in the car will not feel the shock, right, if you have a good suspension system. And the suspension system spring, as you use your car years after years, it can be getting, as you observe, most of you, getting softer, right? So that's basically the time you would start to think about changing this suspension system with maybe just changing the spring. Okay. And there's also many other applications. For example, in the crankshaft system, right? The spring is used as basically a mechanism to close to close the valve. Okay. So, and also, of course, similar, you have many other different situations. Okay. Yeah. Now, what we're gonna look at in this part of the lecture is, okay, so we're gonna focus on compression springs only. Compression helical spring. Okay. So basically means the spring can only be used in the situation of a compression. Of course, there's other situations like you use it in tension, right? But I'm going to look at the compression ones here. Okay. So first, let's look at some of the key parameters relevant to springs. Here's a diagram showing all the key parameters. So I need you to go through all the parameters. You have to be very familiar with this. Okay. Yeah. First one, the mean coil diameter, capital D. Okay, so that referred to the diameter from the center of the wire, okay, to the center of the wire on the other end. So that's your mean coil diameter. There's another dimension, it's called interior diameter. That's basically referred to from here to here, not here, from here to here. So we call that ID, interior diameter. Okay. Wire diameter, that's just the diameter of the wire. Okay. Coil pitch, so that refers to the distance traveled from the center to the next coil. So if you go down one turn, and that's how much distance you will travel. That's the pitch. Right? Very much like threads. Yeah. Helix angle, that's the angle between the vertical line and the inclination of the spring. So the spring basically is a helix, right? So that's, you have the helix angle, okay, like the helical gear, right? Total number of a coil. So this is really important, and I need to emphasize. So you need to be able to count the total number of coils, right? So I'm gonna do an exercise later. So Number coil basically means, let's say you start here. If you go 360 degrees, okay, then you go back to the same, not the same location, but you go back to the same reference place. So and this is what we call one coil, right? Yeah. So given a spring, if I give you a drawing, so you need to be able to count the total number of coils. So start from here. So 1, 2, 3, 4, 5, 6, 7, and then half. So in this case, that's 7.5 number of coils, right? So that's NT. End coil, NE, so I'm going to look at this shortly. So this is referred to a different type of spring. So there's spring, as we can see, there's the ending of springs and looks different. Okay, so this is just a plain ending, and that will be 0. So there will be other different endings. So then we use a symbol 0, 1, 2 to reference to that type of ending. Number of active coil. Number of active coil refer to the number of coil that's actually free to deflect. Okay, so let me just write down this NA here. It is different. It could be different from your total number of coil. Okay, so NA, and this is basically referred to those coils, okay, that are free to deflect, okay, under load. Because some of the ending of the spring, okay, actually pressed, okay, basically closed the gap right here, and then you actually will lose certain number of coils, okay, due to that type of ending. Okay, so that's NA, right? So NA can be different from NT. Just make sure you understand that. Free length, that's easy to understand. When there's no load, then this is your free length. Solid length means when you completely press it close. So press it close until you cannot close anymore, and then the length of that refer to the solid length. Okay. All right. So I'm gonna write down another one here. This is my emphasis. You need to be able to count this NT. So we'll do an exercise later. Okay. Yeah. So how do I find this NA? Okay. For different type of springs though, right? So we will use table 10-1, okay, as a good source, okay, to get this NA here. Here's table 10-1, right? There's different columns here referring to the different ending type, and I'll show you. Given this ending type, and then you have the formulas relating NA and NT, right? And also calculating the free length and solid length, okay, based on your NA value and also the pitch. Okay, so this is a good table to use. All right, so then what will be the type of ending here, right? So this is just illustration of the different types here. For example, this is a plane, so of course this is a plane here. So nothing, basically nothing down to the ending at here. And this one called square, as you can see, basically the two ends at here being square. So now they close the gap at here, right? Yeah. So just basically just a square here. So the square that would refer to, okay, this one, right? Squared or closed. And if you look at the relationship between NT and here, right? So you have your NA basically equal to NT minus 2, right? So if I have a square this, then I can calculate NA based on these formulas. So ground, that will be this one here. So this ground one here is like from the plane, you just sand it flat on the top, okay, that become ground ones here. ground and squared. So essentially, you squared it first, and then you machine off the top one, make it flat. And that's ground and squared. It's very common. This one is very common. Okay, this is a typical spring that is ground and squared, and here. Okay. If you open up some of your some of the system, like even you go to your basement and you look at the pressure control valve, regulator valve. Inside the regulator valve, there is a ground square spring in it, okay, to adjust the pressure. Okay. All right, so let's take a look at a couple examples here. So let's take a look at this one here. This is a plane here, and then if this is the spring that gave it to you. So now let's take a look at the calculation, right? Okay, first step, count the total number of coil. Okay. So let's do the counting. You can count yourself. So this is 1, 2, 3, 4, 5, 6, 7, 8. Right. So your total number of coil is 8. And because this is plane, then NA is the same as NT. Okay. Now I can also calculate the free length, right? Free length is LO, and that's the pitch times NA plus the wire diameter. So let's say the pitch is 5 millimeter. The wire diameter is 3 millimeter. And you substitute into this, you got a 43 millimeter. And I also can calculate the solid length. So if you press completely closed, your solid length according to the table, okay, is D times NT plus 1, 27 millimeter. Okay, this is for plane type of spring. And let's look at this square one here. Right? Again, do the counting of total number of coil, starting from beginning, and move 360 degrees. 1, 2, 3, 4, 5, 6, 7, 8. 8 number of coil. So NT equal to 8. And this is a squared one, so NA, right, equal to NT minus 2, which is 6. So then you can calculate your LO. Okay, so your LO for plane, that would be P times NA plus 1. So 5 times 6 plus 1, 35. And LS, according to the formula, D times NT. Sorry, it's a square. I'm looking at the wrong column here. So we're looking at this one here, right? So the LS equal to D times NT plus 1. So the previous one is PNA plus 3D. So P, we'll still use P is 5, so 5 times 6 plus 3 times 3 is 39. And LS is D times NT plus 1. That's 3 times A plus 1, still 27. Okay. Alright. This is an example. Okay, if I draw a spring, I may not give you the total number of coil, but then you have to be able to count it, and you have to be able to identify the appropriate type of the spring, and then apply the formula from the table appropriately to get the NA, right? Otherwise, these numbers are critical for your future calculations for design or analysis of the spring, right? Okay, so now let's move on to stress in the spring. Okay. The process is still the same, so we first we'll look at the stress, and then we'll look at the strain, okay, and then we can do our design. Okay. So what are the type of stress in the spring? So if you cut off the springs anywhere, if there's a load F, compressive load, and we look at the type of stress on this cross section right here, right? So there are two different types of stress on the cross section. One is called the direct shear. Now let's call it tau D. So that's basically the amount of F, okay, over the cross section area. Okay. So pi cross section area is pi d over 2 squared, right? That's where the 4 comes from. And the other type of stress is due to the torsion. So that's the torsional stress. So if you have a F at here, then there's a distance between the F, okay, at the center, and that's where the torque, right, comes from, and the torque generates torsional shear. So let's call it tau T. Which is TR over J. So T R no R, yeah. T R is right. T is F times capital D over 2. R is small d over 2. J is the polar moments of the area of the cross section. That's pi d to the power 4 over 32. So overall you get 8 times F times D over pi d cubed. Alright, so you get these two stress at here, right? So technically, when you have a cross section, right? So basically identify where the critical locations are. Okay. This is a free body diagram, but if you look at the cross section on the just adjacent to the cross section, then you have basically F going down, and you would have a torque, I believe, torque going, sorry, yeah, probably on the other end, the torque will go this way, right? So basically, at this end, right, you have a tau equal to tau T plus tau D. So that will be your total shear stress. Okay? So if we define a parameter called a spring index, okay, so this is called spring index. Okay? Then when we add these two together, okay, so basically when you add these two formulas together and using C, you can simplify this equation to be this. And Ks at here, okay, is 2C plus 1 over 2C. Okay. So this is basically theoretical calculation, right? Okay. Now, however, okay, experiment shows that the theoretical calculation here considers essentially it's a straight. When you consider the shear stress, especially due to this tau, it's considering that there's like a straight bar, right? Straight circular bar here. But spring is not straight. Spring is actually curved, helical curves. So experiment shows this. So if you have a straight one, is fine. But when you have a curved wire or bar, the interior, okay, actually shows a slightly higher shear stress than the exterior. Okay, so to compensate this kind of experimental observation, the total shear stress tau, okay, is updated by a researcher called the Bergenstrasser. So we update this tau to be, instead of Ks, we use a different Kb, different coefficients. We call it Kb here, and this is still the same. So the Kb at here, okay, is 4c plus 2 over 4c minus 2. And this is called the Bergenstrasser factor. Okay. So we're going to use this one here, okay, for our future calculation, for the shear stress. Okay, I'm running out of time in here, and I can next we're going to look at next lecture. We're going to look at force and deflection. Let me finish the force deflection. Okay, well then we'll save the strings for next lecture. Force and deflection essentially very much like what you have learned when you have a spring. So how much deflection? Deflection is y, and the force is F. How much is F? Y versus F. Okay. So this part you do need. It's not that actually not that simple. You know, we know that F equal to K times Y, right? But the K, okay, is actually derived, okay, based on a so-called Castigliano's theory. The background of theory, you will learn it in your fourth year mechanics material too. But overall, okay, based on this theory, you get your deflection y is approximately 8 times f times d cubed times na d to the power 4 and over the g. So what are they? F is the load, capital D is the spring's mean diameter, D is the coil diameter, and NA, right? So this is where you got to be very careful. NA is the number of active coil, not the number of a total coil, and G is the shears modular. So from here you can derive your spring stiffness, okay, using this formula F over Y, which can be just a D to the power 4 times G, and 8 times D to the cube, and then divided by the total number of active coil. Okay. So this is how you're going to get your spring stiffness, K. Alright? Yeah. Okay, so I think we're going to stop here, and then we're going to look at the strings in the next lecture. Then we'll look at an example. So that will be it for this term. Okay. Any questions? All good? Okay, good. Alright, so stay safe, and almost ending. We'll do a quick review at the end of Wednesday's lecture. Okay. So I think we have already covered the contents. I'll see a little bit about the format of the final exam also in the next lecture. Okay. Alright, so you can go to your next lecture. I'll see you on Wednesday. Okay, thank you everybody.